after I wash your brains for the definition of op-amp, then I would like to wash your brain again for design. Okay, so this is a very important, the most important issue for this chapter. Yeah, how to design op-amp in a systematic way. Yeah, again, in the past, the teachers only show, oh, case 1, then derive, that's it. Case 2, then derive. But what's going on with all those circuits, with all those structures? Nobody told you anything about the origination. Yeah, what did it come from? Okay, so Professor Geiger would like to summarize all those existed or even unexisted op-amps with a uniform, systematic design way. All right, allow me to show you this. Anyway, in the past, for such kind of show and preach, we are teachers, but many of the teachers, they are preachers, okay? They have a lot of time focused on such kind of derivation, very complicated and very brutal force, right? Not much insight to help you design your own. So for such kind of appear and analyze or even preach, that is not a good approach. So hopefully, through the help of Professor Geiger, we can show you such kind of systematic way, to understand the past structures and design the future ones, okay, the new ones. But again, nothing is free. To have such kind of systematic design ways, you need to have some kind of fundamental understanding about the theorems. First of all, symmetric network. Yeah, anyway, if the circuit, or we call network, that is the definition from fundamental circuit theory. It usually call circuit as network. I have no idea why, but anyway, that is their terminologies. If the circuit, if the network is symmetric, okay, you can see to the left, to the right, they are the same. Then you apply your input differentially, positive here, negative here, there, with the same magnitude. Then on the axis of symmetry, everything should be 0. Okay? Not everything. The voltage here should be 0. But why? I think to prove it, you need very strong background in circuit theory and mathematics. But intuitively, you can think that is correct. Okay, why? Since the circuit is symmetrical, right? If you guys close your eye, I help you to flip it, left to right, right to left, right? And I say, hey, come on, open your eyes again. You won't notice anything wrong because it is symmetrical. Okay? Okay? And then, if this is not 0, positive here, negative there, and this is not 0. For example, it is positive, right? So, I mean, according to magnitude, you will see positive to negative and 0 here. That is what we think. If it is not, if it is, for example, it is positive, then it may look like that. Right? 0 here, positive here, negative there. After flipping, this one will become, because it's reversed, it will become negative. It is reversed. Okay? So anyway, for the first time you say, oh, this is positive in the middle. Then close your eye, open your eye, oh, it becomes negative. It doesn't make any sense. Okay? Anyway, only reasonable result is 0 here. And never mind how I flip it. Left to the right, right to left, you always get the same thing. Anyway, believe it or not, if you would like to prove it, then it is a hard work. Okay? And the other one is, for such kind of symmetrical circuit, if you apply some kind of bias current or even bias voltage to the middle, I mean to the axis of symmetry, then we can promise you, for the output, no common mode. It means differential input, you will get differential output. Exactly. Okay, but again, intuitively it is correct, right? And the other one is counterpart network. I told you again and again, but here is some kind of formal definition for such kind of counterpart network. Blah, 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 blah. Okay, yeah, in brief, to see is to believe. What is the counterpart? For any kind of circuit, if you would like to get your own counterpart, then you need to flip it vertically. I mean upside down. And then change the polarity. I mean from N to P, from P to N. From VCC to ground, from ground to VCC, blah, blah, blah. All of them. But if you have something without any polarity, for example, RLC, for resistor, I don't think you have, oh, this is positive and that is the negative terminal for resistance. Nobody will tell you anything like this, right? So for passive component, RLC, they don't have any kind of polarity. 它们没有极性. Okay? So after flipping, they are still the same. But for MOSFET or for BJT, anyway, or even for diode, they have P and N, right? They need to be reversed. Okay? So NMOS will become PMOS, PMOS will become NMOS. And then MPN will become PNP. PNP will become NPN, blah, blah, blah. That's it. Very simple. So allow me to show you. That is what the definition says for counterpart network, but I think that is really hard to understand. Allow me to show you the real case. Okay, so see, this is the original one. And what is counterpart? You just flip it down. Okay? I mean upside down. So VDD becomes VSS. M3 becomes M1, M4 becomes M2. And also, they are PMOS right now. They become MMOS. That's it. Congratulations. Okay? And how about, if you are curious, oh, okay, allow me to show you. How about this? What is counterpart circuit? Flip it up. Okay? So, VSS will become VDD. M1 will become M2, but M1 is MMOS, right? It needs to be replaced as PMOS. That's it. That's it. All right? Very simple. Very easy to realize it. Anyway, the parametric expressions for all those counterpart circuits will be exactly the same. Never mind what kind of result you have, okay? And for the gain, for the bandwidth, for anything, okay? Because the circuit is flipped only, but the structure is exactly the same. You can look them in this way, you can look now in the other way. Supposed to be, they will provide you the same thing, right? So all the equations for this will be exactly the same for that. Maybe the only exception will be if you have, for example, VTP, then it will become VTN. Because P needs to replace by N, N needs to replace by P. If you forget about the polarities, congratulations, everything will be exactly the same. Okay, for example, you have ID equals 1/2 mu N or mu P. Oh, forget about the N or P. Oh, they will be exactly the same. Okay, That is what we mean for this theorem. They should be exactly the same. So congratulations. You don't need to rewrite all the equations for your counterpart circuit. You simply duplicate the original one for the counterpart circuit. That will be exactly the same. If you are curious, remember N should be replaced by P, P replaced by N. That's it. No more. Okay? And then, finally, this is a systematic way to create any kind of op-amp, old or new. All right? How to compose a fully differential op-amp? Differential input and differential output? Very easy. First of all, you have a single-ended amplifier. Okay? We call it a quarter circuit, 四分之电路. Only a quarter of the whole. Then you have its counterpart circuit to compose half circuit, and then flip to the left or to the right, I don't care, to get the other half. Overall, you apply in the middle. I mean, you apply your bias. Never mind, bias current or bias voltage to the axis of symmetry. Then you can compose the fully differential op-amp. That's it. No other secret. But why? There are two major reasons. First of all, you will know for all those existed op-amp structures, all of them can be constructed with such kind of systematic way. Okay? The second reason is for the new one, you can also create it by yourself. But you only need to focus on this, because for the counterpart circuit, the performance, all the equations are the same. And how about the left and the right half? The same, right? It means what? The overall performance is decided, is dominated by the quarter circuit. If the quarter circuit is good, I mean again, then no worries. The overall circuit will be also very good at the gain. If, on the contrary, if the overall gain is no good, then you only need to enhance the quarter circuit. That's it. Because you enhance it, all the others will be also enhanced. They are exactly the same in theory. Okay? So it means what? For your own design, you don't need to focus on the whole circuit. No. You only focus on only one quarter. Then you can make it. It will simplify very much your own design or your own optimization. Bingo. That is the major two reasons. Okay? And also, it offers you another possibility. That is what you never learned from your microelectronics. Okay? Not only bias current, but also bias voltage is possible. All right? But I need to warn you. Why? People seldom come here. Simply because input, the transconductance will vary a lot according to the common mode input voltage. We would like to amplify the difference. For the same thing, we call it maybe VICM, okay? Input common mode voltage. Here, the higher input common mode voltage means the much larger transconductance. Okay, but anyway, for the current moment, I can think about two major applications for this. One is as large gain as possible. I promise you, this one will provide much larger gain than there. Okay? And then the other one is the VICM is fixed. For some application, it is fixed. No worries. Okay? That's it. Maybe there are the other possible applications, but you can think by yourself. Yeah, anyway. And again, yeah, I can help to refresh your mind. Hey, how about the VICM? What is the impact of VICM, input common mode voltage, for this structure? You can see, if I increase the common mode voltage for input, I push it up. Right? For this one, you can see for the usually that is a simple current source, just like its curve look like this, right? Yeah. So for the current source, the major function is to keep, for your own design, to keep the output current as constant as possible. Right? So you can see, if you increase, if you push the VICM upward, your current source will push it. Yeah, I mean the VDS here will be pushed from here to there. Okay? Okay? And how about the IDSS? In theory, it is constant. In practice, it only increased a little bit. A little bit. If the RO is high enough, right? So what does it mean? According to GM actually is dependent on this. Okay? If you don't fix, right now, according to VICM, the IDSS of this will be changed, right? But GM is proportional to this. As I showed you already, it operates here. Even you increase your VDS from here to there, very little increase for IDSS. Congratulations. After the square root, very small change for your GM. Congratulations. Congratulations. Okay? Never mind what the input common mode voltage is. The GM of the differential pair will be kept about the same. Alright? But it doesn't happen there. Totally different. Okay? Anyway, what I would like to refresh your mind, what is the mechanism to keep GM almost constant, about constant, yeah, for this structure, through the help of current source. If you goes up, then current source will help you to push the node voltage here to follow your step, to keep VGS about the same. Congratulations. And this is the reason why GM will be kept almost constant. Okay? Did you notice this? Then I help you a lot. Okay? Even though all of you study microelectronics, maybe most of you get A or A+, but did you get such kind of good enough understanding? Unluckily enough, most of the students, they don't. All right? So try to train yourself. Yeah. So for my new students, one of my I have only 2 recommendations usually. The first is to reread the microelectronics before entering my lab. And the second, to enhance the English. That's it. 2 major. Yeah, 2 major issues for them, for the goodness of their own future. Yeah, anyway, right now you know already the secret. Only focus on this. Yeah, it will be very good for you. Okay, so this is the quarter circuit. Maybe we can go back here. the quarter circuit, and you compose the counterpart circuit. Compose quarter circuit and its counterpart. We can have the half circuit. Flip it, get another half, and in the middle, apply the bias current or bias voltage. Good enough. All right? Yeah, and then for your analysis, for your own design, it is much simplified because the overall performance is decided by this one. Good quarter circuit will generate good fully differential op-amp. Bad quarter circuit will generate bad op-amp. That's it. Okay, focus on this. But how to, when you focus on this, what do you need to know? Again, because you apply V in here, right? Right? We convert input voltage into output current. So you need to know transconductance. Never mind what's inside, I don't care. A black box. You only need to know the transconductance. And then know the output conductance or the output resistance. Then what is your output voltage? Or what is the voltage gain? Again, Gm by Ro or Gm by Go. Right? Output conductance. That's it. That's it. Your design, your logic thinking will be much, much simplified. And again, if the overall gain for your differential amplifier, for your fully differential op-amp is not large enough, then we come back to check here. You either increase it or decrease it. That's it. Focus again only on the quarter circuit. Increase is transconductance or decrease is output conductance. That's it. Okay? Piece of cake. Piece of cake. Yeah, anyway. I think for common source, I derived it already. Okay? Yeah, this one. But why we have this one divided by 2? Simply because the input, the differential input is applied from here to there. So you only get 50% of the input. That's it. Okay? For all the others, except for 2, you can see, I thought this for you moments ago already. Right? So right now the only difference is divided by 2. But I explained already. So how about the DC gain? Except for this, I show you already. And how about the bandwidth? I show you already, but divided by 2. Okay? That is for single ended output, but this is a fully differential structure, right? So we take VO plus minus VO minus. Congratulations. The magnitude of this and that will be the same. But this is positive, that is negative. So for differential output, the magnitude will be doubled. Okay? Why the magnitude are the same? Again, go back to see what happened. Yeah, here is the for the left, and that is for the right. But they are exactly the same. We only flip the circuit to the right. Right? So what is the gain here should be exactly the same there. Right? But you apply positive input. You apply negative input there. So the sign will be reversed. That's it. Okay? Okay? That's it. Yeah. According to symmetry, left and right should be the same. So, congratulations. That's it. That is the overall gain and bandwidth product, gain bandwidth product. Okay? Yeah. So, from the very beginning, the simplest one. And what is the simplest quarter circuit? This one. Common source. Right? Common source amplifier. That is the simplest quarter circuit. Yeah. Then what is this counterpart circuit? Flip it from NMOS to PMOS. corner circuit. So we flip it to get the counterpart circuit. But for each half, because we apply our input differentially, one for left, the other one for right. Okay? So for the half, this is the half circuit, right? We have only one node to apply your positive input. So how about the other one? It should be fixed. That's it. Okay? But allow me to show you. Allow me to remind you. Actually, if you are happy, you can apply minus V in also here. Okay? In this way, the gain will again be it will be substantially increased, but the GM here won't be constant because according to the overall structure, see, we only apply bias current here. We don't apply bias current there, right? So the GM can be kept about constant through the help of this current source. But without current source there, the GM will be varied a lot, as you like. Maybe say, hey, look, I can apply another current source there. Oh, yeah, you are really smart. But the headroom will become sky large, really large. I don't think you can afford it. As you like, I don't care. All right? So, if you would like to apply VI plus, VI minus, VI minus, VI plus, and also another current source there, the gain will be much higher. Okay? But the input operation will be reduced. Yeah, okay. Now I have another important meeting. Let me see. Oh, 12:20. Oh, 12:10, 12:20, right? But 干什么的？ Wait a moment.